Okay, so today's factoring lesson is on how to factor a difference of squares. And we have two goals for today. One, be able to recognize a difference of squares, and two would be able to factor a difference of squares. So we have to be able to identify them correctly, which is actually a little trickier than it might seem at first. And then once we've correctly identified a difference of squares, be able to follow the correct factoring pattern for that. Now, let's look at our first example here, because this is a great, simple example of what a difference of squares is. X squared minus 4. This binomial is an example of a difference of squares. And that's really what a difference of squares typically is. It's a binomial, so it's a two-term polynomial that contains two perfect squares. Now, let's talk about what two perfect squares are. Okay, well, x squared is a perfect square. And the reason why is because it's a square of x, right? So x times itself. If I take x and multiply it by itself, in other words, if I square it, I get x squared. Therefore, we can say that x squared is a perfect square. 4 is a perfect square because it's the square of 2. 2 times 2, or 2 squared, is equal to 4. So these are both squares, as I've defined right here. This is a square and this is a square. Therefore, they're two squares. Now, the other emphasis here is on the word difference. It must be a subtraction problem. It has to be x squared minus 4. If, for example, we had over here x squared plus 4, this will not factor. This is actually prime, by the way, and we can elaborate more on that later. But for right now, just understand that this is not a difference of squares. Yes, they're both squares, but it's a sum of squares, and that will not follow the factoring pattern that I'm about to show you here. Now, the factoring pattern is actually very simple. It just says this here, that, okay, if I have a difference of squares, for example, a squared minus b squared, so this is any difference of squares where a and b can be variables, they can be integers, whatever. If we have a difference of squares like this, it follows this factoring pattern, a plus b times a minus b. So if we take our first example, x squared minus 4, this simply factors into x, I knew something sounded wrong about that, x plus 2 times x minus 2. I take the square root of x squared, which is just x, and I put that in each term. And then I take the square root of 4, which is 2. So we write it as a product of x plus 2 times x minus 2. And of course, I could multiply this, right? I could sort of distribute everything, and you'll get x squared. If I do that, I get minus 2x plus 2x. And then I would get plus 2 times negative 2 is negative 4. And I would simplify that. These would cancel out, of course, and I'd be left with x squared minus 4. So you can see it works, right? Because here it is again, x squared minus 4. But the simple factoring pattern is just we write the x in each set of pair of parentheses, and then you write plus 2 and minus 2. Now, this works for any difference of squares, and I'll show you a couple more examples in just a minute. But in case you're wondering, well, why does this work? Because this isn't how we've been factoring. You can follow the same factoring pattern that we've been using. So here's that standard form of factoring, right? Where this is our quadratic polynomial, ax squared plus bx plus c. I could write this in that form and factor it the same way that we did on Monday and Tuesday. Here's how that would look. I would take my first term here, x squared. Now I don't have any x term, so I'm going to invent one. I'm going to put plus 0x, and then minus 4 would be the c term. And hopefully you can see that this here is equal to this. These are the exact same expression. I just inserted a 0x. This has no value, but I write it here just so you can see it in this format. And then we would factor this the same way we did factoring on Monday and Tuesday. In other words, I'm looking for factors of negative 4 that have a sum of 0. Well, what are those two? Well, it would be 2 and negative 2, right? 2 times negative 2 is negative 4. 2 plus negative 2 is equal to 0, which factors into x plus 2 times x minus 2. So, this is the longer way of doing it. This isn't how I'd recommend it, but just in case you want to see the connection, there it is. Now, just a couple more examples of factoring a difference of squares, and then we'll call it good here. Here's another simple one. n squared minus 64. These are both perfect squares, and this is a difference. So this simply factors into n plus 8 times n minus 8, because 8 is the square root of 64. Go ahead and try this next one here. What do you think this one's going to be? I'll give you a second. Y squared minus 25. How does that factor? Well, square root of y squared is y, plus 5, because 5 is the square root of 25. And then we have y minus 5. Now, this will also work for any variable with an even exponent, right? Because m to the fourth, for example, m to the fourth is a perfect square, because I can get m to the fourth by squaring m squared. M squared times m squared is m to the fourth. So that's a square as well. This is where it starts to get a little more complicated. 36 we know is a perfect square. So this will simply factor into m squared plus 6 times m squared minus 6. All you're really doing here is just cutting the exponent in half and splitting it between the two polynomials. One more that's a little tricky here. If I go down to this 9n squared minus 16. This one is also a perfect square because the coefficient 9 is also a perfect square. So you can see that these will get more elaborate, and that's okay. The only rule for this is that every single part of the binomial has to be a square, or else this won't work. And of course, it has to be a difference as well. So I take the square root of 9, which is 3. I take the square root of n squared, which is just n. And then we're going to take the square root of 16, which is just 4. And it follows that factoring pattern. So it's just going to be 3n plus 4 times 3n minus 4. So we'll look at a bunch of examples together when we meet this morning. But here you go. It's really just taking every single one of these binomials and following this factoring pattern here, where a squared minus b squared is equal to a plus b times a minus b.